Okay, Matt Roscoe here at the University of Montana in Math 326 number theory, second part of our two-part video for my replacement lecture. We were talking about primes and in particular the fundamental theorem of arithmetic, um, and really I asked you to go ahead and review the proof in your book and to take a quick look at that using a fill-in-the-blank type of an exercise, hopefully make you critically think a little bit more about what's in the theorem and why it's true. One profound, I guess I should be careful here, hold on. One thing that you should be aware of is that you can write any positive integer n uniquely in canonical form. So it's p1 to the k1, p2 to the k2, p3 to the k3, pr to the kr, where for I from 1 to r, each ki is a positive integer and each pi is a prime, and each of those primes are successively strictly less than the primes that succeed them. So this basically resolves the problem of uniqueness with primes and prime decompositions. Let me just make sure you understand what's meant here. So for example, if I take the number, let's try 80. 8 times 10, 2 times 5, this is 2 times 4, and 2 times 2. So what does that mean? That means 80 can be written as 2, well, let's write 80 here first. 80 can be written as something like, let's say, 2 times 5 times 2 times 5 times 2 times 2 times 2. Of course, another way we could write 80 would be 2 times 2 times 5 times 2 times 2. And of course, these representations are not unique because the 5 is sort of in a different place. But what I guess this particular statement says is that if we write things in canonical form, so we start with the smallest prime factor first, that's 2, and we raise it to its proper exponent, it's 4 here. And then we go to the next prime in the expression, it's 5, and we raise it to the proper factor, which would be 1, or an implied 1 if you just leave it out. Then this particular form is what we think of as unique because we've restricted it to canonical form. And when we're restricting it to canonical form, then the expression, the numbers, I guess, identity written in prime product form is now unique. And here's the profound implication of the FTA that we'll end the lecture on. And it turns out that this is one of the places where understanding prime numbers can really help us to construct basically a whole number universe, and that is this universe of irrational numbers. And really, the understanding of irrational numbers and something that's not, expressible as a ratio of two integers relies on our knowledge of integers and number theory, which is kind of a surprising result. So let's go ahead and prove this statement. I guess I need to move over to my doc cam, make it as large as I can get it for you, and let's go ahead and see if we can prove this large statement. So hypothesis is that very short and sweet, root 2 is irrational. So what does this mean? It means that root 2, i.e. Root 2 cannot be expressed or is not equal to some a over b, where a and b are elements of z, and I guess we have to say that b is not 0, right? So it's irrational. I always tell students when I teach them about irrational numbers, the root word of irrational is actually ratio. I think this word gets confused a lot with its use in common English, which means nonsensical. It really means irratioable to us in math. You can't write it as a ratio of two integers. So to say something can't be written this way, I hope that this gives you some idea of a method of proof. When you say something can't be written this way, usually that's an indication of some sort of a contradiction technique. So here we proceed by contradiction. Let's assume that root 2 is rational. If it is rational, then we can write root 2 as the ratio of two integers, a over b. And since root 2 is positive, let's restrict it for a and b in the positive integers. And let's also restrict it to be written in lowest form. So let's let the GCD of a and b equal to 1. I mean, if it's not in lowest form, we can certainly make it lowest form. So we can say that here. And then let's just say and that b is greater than 1. So if b was 1, then what would be the point of writing it as a ratio? It would be a whole number, right? We're going to assume, I guess, that root 2 is not an integer, and I think that's a fairly easy assumption to make, because you can certainly find root 2 on a number line by simply looking at the diagonal of a square, which we know to be root 2, and see that it's definitely between 1 and 2, so it's non-integral. So let's go ahead and square both sides to get, so if I square the root 2, of course I get 2, and if I square a over b, I get a squared over b squared. And if I solve this so that there is no more, I guess, fraction bar, I can multiply both sides by b squared to get 2b squared equals a squared. So now we have a statement that shows, an a on this side, a b on this side, and a 2, I guess 2 a's, 2 b's, and a 2. So now we can make some statements about divisibility. We can see that b is a factor of the left-hand side. Certainly b is a factor of the left-hand side. So it must be a factor of the right-hand side. So in other words, if there's a factor of b over here, then there must be a factor of b over here. And one of the yeah, so if it's contained here, it has to has to be over here. So so what that means, I guess, is that that b divides a squared, right? So in other words, if there's a factor of b over here, it's got to be over here as well. So b must divide a squared. Now, the FTA guarantees that there exists some prime, let's call it p, such that so the FTA guarantees that there exists some prime p such that, I don't think you're going to be able to see them both, I'm sorry, p must divide a squared, right? Or sorry, p must divide b first. Let's say we're going to think about b first. So p divides b, but since b divides a squared, we get what? Well, we get that p must divide a squared as well, right? Which can be also put this way: p must divide a times a, right? So now we have a situation where p divides a product, and since p only has 1 in itself as a factor, it must divide one of these two. That's the theorem that we proved at the start of the chapter. I guess by our theorem proved earlier. And we have arrived at a contradiction. And I guess what I'm going to do is I'm going to end it right here and ask you to write the rest of the proof. What is the contradiction that we've just proven here? And what I'll tell you to do is to go ahead and check the PDF of my notes where I will finish the proof on my own. But what is the contradiction? Because you should definitely explain what we've contradicted in our assumption earlier here, and show that since it's contradicted, that it leads to absurdity, that that our assumption that 2 is rational must be false, and therefore 2 must be irrational. So I'll leave it there and ask you to finish the proof on your own, and then to check the notes to see if you came to the same conclusion as I did. And I look forward to seeing you on Monday after I get back from sunny Orlando. Have a great weekend, everybody, and we'll get ready for test number 1 on Monday when we review, and Wednesday when we take that exam.